I think we can start officially. Welcome back, everyone. So for today's class, our goal is to finish off the section 5.3 notes, and we should be pretty well on track for that. And then we're doing our last section ahead of exam 2, which is going to be section 5.4. I think that one will likely be finished either Monday's class, but more likely Tuesday's class of next week. Then next week after Tuesday's class, we'll just switch gears into preparing for the second exam. So we'll be reviewing on Wednesday and Thursday's class. So that's our goal so far. We look forward into the week. On this midterm week, we'll be reviewing on Wednesday and Thursday, and then we'll return for our second exam on Monday, October 16th. So it'll cover section 3.4, think box plots. Section 3.5, that's when we're using the empirical rule, or the 68, 95, 99.7 rule. These three sections right here, these are all going to be about least squares regression. So it's really going to be focused on dealing with that regression line. Really, that was the whole goal of section 2.4 and 4.1, to get to the point where we're comfortable finding and working with that regression equation. That all of this we're familiar with, we're getting through probability. And so it's pretty much going to be anywhere between 4 to 6 questions, probably more like 5-ish, just to keep it well controlled for a 50-minute exam. Well, that's our rundown on the notes so far. Any questions or comments, folks, at the moment? Okay, before we jump back into section 5.3, I just wanted to mention that there are quite a few definitions, formulas, and those kinds of things, but occasionally one formula is just more important than the others. Well, really two in this case. It's these two that are in the boxes here, and on the actual notes, let me show you where they look like or where they are. The first really big and very important formula is this one right here for mutually exclusive events. So I'll put a little star on it on the notes just to indicate where it is, even highlighted it for good measure. And this is only if we know with complete certainty that the events A and B cannot occur together. That makes them mutually exclusive, and that makes them come out to a probability of 0 if we do an intersection. So this is reading probability of E and F occurring together has to be 0, since if they're mutually exclusive, it's impossible for them to occur together. Then the next big formula, we actually haven't used just yet. We talked about the definition of independence. And now right here, this is the independence formula. Its explanation actually requires section 5.4. So I want to turn back to this when we're in that section, just to give a description of why does the formula look the way it does. It is kind of an unusual formula, but it says if we take the probability of E intersect F, E and F, that's just the probability of E times the probability of F, and then we're done on this one. So equally invaluable formula, but this one hinges completely on the events E and F must be independent. Let's put in brackets what that means, just as a loose verbal description. E and F being independent events would mean the probability that F occurs does not depend on whether or not the event E occurs. So if knowledge about E occurring or not has no bearing on what the probability of F is, we'll have independent events. We looked at a couple simple scenarios with that, and we'll see another one on example 7. But for the moment, here's a pretty routine web-assigned kind of problem, which would require this formula above. Well, any questions or comments, folks, before we try out this new situation? Okay, so we have our formula ready to go. We'll use that right when it's required. And here's what example 6 looks like. The context here is really kind of minimal. This one looks like it was not a real world problem, but that's okay. It says a construction firm bids on 2 different contracts. We're going to call the first contract E1 and the second contract E2. Then we have events. We'll say E1 is the event that the bid on the first contract is successful. So let's color code that one. I'll go with blue here. E2 will be the event that the bid on the second contract is successful. And nothing here says they can't win both contracts. I mean, it would almost imply it, right? That they're getting one or the other. But maybe this company, if it does win both contracts, maybe they just hired more people, some temporary workers, and they just take the money from both. So it looks here like it's plausible they could happen together. These are not mutually exclusive. But it says here, the events E1, E2 are independent. Now, how do we know that? Well, we have no idea. We're not the construction company. We're not in charge of the bids, but they told us these are independent. And thinking from a standpoint of maybe fraud or something like that, if there was independent boards reviewing the company or making the bids on contracts, then yeah, the decision to win E1 may have nothing to do on the decision to win E2. They're just looking at the merits of each bid and the company for either one. So it's plausible we have independence here. But the moment they say that, something amazing is going to happen in the hypothetical 1000 table. But let's first start from first principles. Part A, we want to construct the table, and we already have two probabilities indicated. Probability we win the E1 contract is 0.4, and the probability that we win the second contract is 0.3. So we can go to the margin now and take 1,000 times probability of E1. This comes out as 400. Take 1,000 times probability of E2. All that really happens is we're taking 1,000 times the 0.3 that you see there, and we get a value of 300. So we have two counts, but if we start our table, we kind of get stuck. Nonetheless, let's write out the table and see what it looks like just based off those two counts. So the table could begin like this. It's always going to be these three horizontal line segments, then three vertical line segments. I'll put total here, in those specific corners. And in this bottom right corner, we'll put the overall count of 1,000 hypothetical cases. Next, I'll throw E1 here. This is the company wins the first contract. E2 complement means they lose the second, or excuse me, that was incorrect. I think those subscripts are mixing me up. E1 on both of them. 1 and 2 made sense for a minute until I looked at it a little bit more closely. So E1 complement is saying they lost the first bid. Likewise up here, E1 would mean they won that first bid. Or excuse me, let me try again. E2 means they won the second contract. E2 complement means they lost the second contract. Geez, those 1s and 2s on E1, E2, they kind of mix me up. I'm probably not going to write a question that goes that way. I mean, me alone, I don't like the subscripts in this kind of problem, but it is what it is. So we've got the information in after a couple undoing the work. Control Z. Now the value of 400 we'll place right over here for E1. The value of 300 cases we'll put under here for E2. And we're kind of in good shape at this stage. Any questions, folks, to this stage of the table? Okay, I mean, we can put a couple more numbers down if we really want to solve it, right? We could put a number here. It has to be 700 so that the row total comes out to 1,000. So 700 would work. To make the column total come out to 1,000, we'd have to have 600 cases over here. But now we're just completely missing the required information to find out what goes in the middle. There's nothing we can do. But one thing we haven't done yet is we never used that information, which is a decent strategy on a web assigned problem or a quiz or an exam problem. If there's a portion of the problem you notice that you never used, that was never brought into play, then that might be the problem of why we can't solve this portion right here. So let's use the information on independence. We're told straight out, if the events are independent, then by the formula above, we can find the probability for an intersection. Here's how it's going to go. We want to kind of circle it this way, just to indicate we're using that information. Then probability of winning the first contract, that's E1, intersect winning the second contract, that's E2, That will just turn into, by what the red dot is saying here, we take two more probability statements and just multiply them together. This is equal to probability 1 multiplying probability E2. I'll put a solid dot right in the middle just to really emphasize they're being multiplied together, but that's not required. That's just to emphasize. Usually the formula is written this way when they're just placed next to each other to indicate multiplication. Still doesn't give us a number, but we can come over here and just look up the values. At this stage, we're making two substitutions. Right where it says probability of E1, we go and find the value, 0.4, and we drop it down right here. Notice that once we find the value, we drop the P function. We don't need to say probability any longer because that's the probability down below, 0.4. Likewise, for E2, it had a value of 0.3. I need a different color then. So take the 0.3, drop it into that parenthesis. And then we'll just multiply that through. 4 times 3 is 12. There's two decimal places to account for. So this becomes 0.12 altogether. Now, since it's a hypothetical 1,000 table, we'll multiply that value by 1,000 and get this result. 1,000 times the probability of E1 intersect E2 comes out as a count of 120. Now, amongst these four boxes right here, any volunteers for where the count of 120 ought to be placed in? So this section right here? Yeah. Exactly. So we intersect right there, thinking in terms of the table, and it must go right here. That's always the location for the count of 1,000 times any intersection. That look all right to folks so far? Awesome. So essentially, without this formula that we put in as a star, there is no way I could solve this hypothetical 1,000 table. But now that we have this key value, 120 in purple, the other three values around it can be solved immediately. Any volunteers for what should go right here by that red dot? Exactly. So that should be something like 180. Let me know if my numbers look kind of strange. Usually when you're tired at the end of the week at a night class, arithmetic is the first thing to go. So on this one, I'm going to take 120 away from 400, place the value here. That should be a 280. Then let's do it again. To the right is 600. Subtract the value of 180 to the left. Then in the middle, we'll get, let's see, that should be a 420. So we've got it, folks. It's not a bad idea to double check your work just to make real sure it comes out correctly. So here's what my check would look like. I'm going to go amongst the columns. Columns means going downwards. So I'll take 120 plus 180. I've got a value of 300 as expected. Now sum this column, these two entries, 280 plus 420 comes out to 700, so we're in business. 400 per 600, we shouldn't need a calculator for that, should come out to 1,000. So to me, that'd be enough evidence to say we have an accurate table to that stage. Well, we did it, folks. That's the entire hypothetical 1,000 table. Any questions at the moment on getting through it? Okay, and now I'm noticing in my part B, kind of a silly question in a certain sense. We'll answer it because, I mean, why not? Let's put an extra part on this just so we can have some more practice. So in addition to part B, let's call this part C, not copyright. How we fix that? There we go. Let's say for part C, the question would be, what is the probability that the construction firm loses the bid on both contracts? I'll put this in red just to indicate, again, that was something new on the notes. I think I should have added that sooner before I put those notes on Moodle. Sorry about that. So part B still is an interesting question. Probability of E1 intersect E2. Here's the reason it's kind of silly. We already did it, right? It's right here, 0.12. We did it by using the formula that's up here in yellow, but because we have the hypothetical table that's down there, how about we just try it again? So probability E1 intersect E2. That's going to be this location on the table where E1 and E2 intersected. We get a count of 120 divided by 1,000. And yeah, after we do that division, we get 0.120. And that would be the probability of that one. But the thing that's new about this problem is we still have to give a practical interpretation to it. So we'll do that next. First, any questions, folks, on getting the 0.12? I kept the 0 for no reason in particular, but just as a reminder, the decimal place here moved to left 3 positions when we divide by 1,000. But any questions so far? Okay, let's give a quick and dirty interpretation for this then. The 0.120, we can multiply it by 100. Now it's a percentage. And we'll say there is a 12% chance that, now E1 means they won the first contract. E2 means they won the second contract. And the intersection symbol, if we're writing this out in words, we'll just give a literal and to that statement. So there's a 12% chance that the firm won, you could say the first contract and the second contract, that'd be completely fine. Or you could just say both contracts. That implies an and with the intersection as well, if you prefer. So it doesn't always have to be completely formulaic. I'll go the formulaic way. We turn that to percentage. Over here, we'll say won the first contract. Where the intersection symbol is, I'll just put in and. Here, we'll look up what it was. They won the bid on the second contract. So I'll say and won the second contract. So it does it for us, folks. And I'd say the trickiest thing about this interpretation is we need to know when we see this reversed U, not really a U, but this intersection symbol, it means we put down this word and right here to correspond to intersect. Well, that's an entire problem down. Let's try out the part C next. First, any additional comments on getting through that one? Yeah, go ahead.
So when we're like calculating when it has the intersect, it's just the one value, and then if it's the union, then it's like we're doing like the row.
Yeah, exactly. Yeah, and a good place to take a look when you're solving these kinds of problems, say WebAssign or a quiz, is earlier in these notes, there were up to 10 pages. So there's a lot of stuff here. But this page right here is kind of like the cheat sheet of where to grab the right cells versus intersect or union, like in this case. So like you said, if it's A union B, we take all the values for the row A, all the values for the column B, and just plug them in. Other questions about that so far? Okay, let's see if we can get to the bottom here. So we've got that question down. Let's try off this next one, part C. And just a reminder with some of these questions, essentially there is 2 kinds of formats. Sometimes they say calculate a probability statement like this one, but we have to know what it means, and that will almost always be followed up with give a practical interpretation. But part C is different. This one starts with an interpretation of what we're about to calculate, and the first thing we ought to do is write down the probability statement that goes along with it. So in a certain sense, this one's kind of backwards. It says, what is the probability that the construction firm loses the bid on both contracts? Now the word both is implying an and, so we can put an intersection right here. There is 2 contracts in question, E1, E2, but I'm still missing some information in that probability statement. I mean, we've already calculated that. Anyone see what needs to go next to E1 and E2 to make this fully correct? Exactly. When it says loses the bid, that's contrary to when they won the bid. So we'll put here the complement. and the complement here as well. Only because they said loses, we had to go that direction. Then going back to the table, I'll use the temporary highlighter to just find the right count. Go to E1 complement, that's this row. Go to E2 complement, that's the second column up here. And where the highlighting yellow overlaps, right here at 420, that's going to be our intersection count. So it'll be 420 right here, divided by 1,000. That means we'll have a probability of 0.42 on this question here. Because the question didn't start off with a probability statement, you could interpret it, but really it should sound the same as what the question was. So in other words, if I gave an interpretation to this, I would say there's a 42% chance that the firm loses the first contract and loses the second contract. In other words, loses the bid on both contracts. So we've got it, folks. That's the way to get through this particular problem. Any questions at the moment on the conclusion to example 6? Okay, so at the moment, there are two key and vital formulas. This is the second one, and you can go through the notes just to find these things. I put highlighting and stars around them just to indicate. Now let's try one last question. The last question is going to use independence again, but in a different sort of way. Example 6, it just told us, it threw it at us, E1, E2 are independent. But occasionally we'll have problems where we kind of have to decide that for ourselves. So let's go and grab the definition just to make it available. I went too far. There it is. I'm using this definition in front of example 4. I'm just going to put it right here. I guess we have a good amount of stuff right here, just to make it available. Okay, so here's our last example in the notes. Congratulations, folks. I'd say section 5.3, probably one of the tougher sections in this entire class. We're almost through it. 5.4 is not as bad. So the problem says, on example 7, each time a class meets, the professor selects one student at random to explain the solution to a homework problem. This actually happened to me in real life. I had a professor that actually did that. Randomly, one person selected, they would go to the chalkboard and just try their best to solve a problem. It was horrible. I'll never do that to you. But now it says here, there are 40 students in the class and no one ever misses class. That's just to make the problem simple, so nothing weird happens. Luke is one of these students. And we want to know, what is the probability that Luke is selected both of the next 2 times that the class meets? You can imagine if that was you, you just feel like you're being picked on, right? That the professor really has it out for Luke and they're putting Luke to the fire twice in a row. We would like to find the probability of that actually happening. Well, that means we need some events. So let's start defining some events. This is all about being selected to put down a problem. And we can say A, Luke is selected. Next class, he's selected to do the problem solution on the chalkboard, but I'll just say is selected, leaving the rest of the context to carry. And we'll go B, Luke is selected on the class after the next. So in other words, he's just selected twice in a row, next 2 classes. Next thing we'd like to do is, well, we need to get at this question. This is the more complicated question right here. But before we get to finding the probability he's selected twice in a row, we can still calculate the probability of A just right here. So let's do probability of A. Now we're assuming this is done in a fair way. There's 40 students. So imagine you have a die with 40 different sides or a random number generator, selecting one number from 1 to 40. That would mean these are equally likely events. There's 40 different outcomes corresponding to the 40 different students. A is the probability, or excuse me, A is the event Luke is selected. There is only one person like Luke, so that would be 1/40th altogether. Does that make sense to folks on getting that probability here? Awesome. So we're really just saying there are 40 students. That's what went to the denominator. We're only selecting one student, Luke. So one possible outcome out of the sample space of 40 possible events. Really, we're just using the equally likely idea once again. And likewise, if we calculate the probability of B, it goes the same way. It's the same class, all 40 students are there each and every time. So probability of B is 1/40th as well. Okay, well, now we're going down to this question. We want to know, what is the probability Luke is selected both of the next 2 times that the class meets? The word both there can be considered to be an and statement, which would mean we're dealing with an intersection. Let's put that right here just to emphasize. Both is conflated with and in this context, which means we'll be using this symbol for intersection. And the arrows go both ways. So if you're using intersection, you're talking about an and, which means you probably have something like that in the problem. So to answer the overall question, we'll say probability that the outcome or the event A occurs intersect the event B. Now, whatever this comes out as, well, that will be the answer to this overall question. Now, here's where I would get stuck. I mean, there's not really a formula here, right? They didn't tell us straight out if these are independent events. We have to decide that for ourselves. So if they're independent, we can use that formula right there and we're pretty much done. But would you believe they're independent events? It's kind of a tough question in a way, right? Let's go back to these definitions. It says 2 events are independent if knowing that one event has occurred, think of that as the event A, does not change your assessment that the probability of the other event has occurred. So if A occurs, if student Luke is selected on the next class, would you say the probability that he selected the class thereafter is still 1/40th? Probably, if he's doing everything fair, right? If the person who's in charge of selecting the student, is taking another randomly selected number from 1 through 40 on the second day, as well as he did on the first day, then really in spirit, this is no different than what's happening right here when we're tossing a fair coin. I mean, tossing a fair coin has 2 outcomes. That's selecting 1 out of 2 possibilities. This is just a larger problem. We're selecting 1 out of 40 possibilities. So whether A has occurred or not, for the coin, we get a 50% chance. But for selecting a student, say Luke 2 times, that should be 140 times 140 altogether. So this one is a situation where we have independent events. They just didn't say it altogether. That means we can use that formula, put a star on it again, just for emphasis. And now we can write that this is equal to the probability of the event A multiplying the probability of the event B. But let's put this here, just to be specific. This formula only can be used, that looks like con, let me make it be a can, be used here since events, they were A and B, are independent. No matter what, if Luke is selected the first class, probability of getting selected on the second class doesn't change. And that tells us the probability of the event B did not depend in any way on event A occurring or not occurring. So now that we have that in play, we can now say, multiply the 2 values together. The first value for probability of A, we just put in the number, 1/40th. Then it's multiplying probability of B. We make another substitution. It's kind of like doing IQR or doing the 1.5 IQR rule of thumb. There's just lots of substitutions here. In place of probability of B, substitute it with a 40th again. Now finally, we can crank this out, just multiply the two numbers together. In the calculator, there's a lot of ways to do this. Let me show you a couple options. If you want, you could just type it out verbatim. We need a 1/40th times 1/40th. And we get a very small number. Another way to do this to save a little bit of time is you could go 1 divide by 40. If it's 1 divided by 40 times the same thing, it's really 1/40th squared. So you can click on that button. Let me make that a little bit bigger. Click on that button, it'll square the 40th. It'll get the same exact value. And a third option is you could just put in 1 divided by 40, hit enter here, and that's a 40th, exactly 0.025. Hit the power 2 button and it's squaring the prior result. And we're getting this, no matter how we do it, we're getting scientific notation. This will happen, we've seen it happen once. In WebAssign, I think it could happen around 2 or 3 times, depending on the section you're in, or chapter you're in rather. So I'm going to put this down on paper and then write out 6.25e negative 4. A mysterious looking number, 6.25. In place of that e, negative 4, what it really means is times 10 to the power of negative 4 through scientific notation. So that's what this portion is really saying. For multiplying by 10 to the power of negative 4, the decimal place that's right by the red dot moves left 4 different positions. So that's our next thing to do. So back here on paper, it's going to be, I'll put the 625 here. I'm going to delete that arrow in a moment and just trying to account for how many places we move the decimal place. If it's moved here, that's 1 place. Moved here, it's 2 places. Oh, that's really hard to keep that red dot steady. And if we put it here, counting these off, that's 1, 2, 3, 4 positions to the left. So 10 to the power of negative 4 is 0.0006.25. But the problem is still not done. First, any questions at the moment, folks, to get to that standard form of the number? Okay, once we get here, I would be totally fine with that number. And there's a good chance that WebAssign is okay with it too. Because we have great accuracy, it's just that we have 1, 2, 3, 6 decimal places of accuracy. We want to round it to 4 decimal places, so let's make that our last maneuver. So the end answer, after rounding, if we're rounding to 4 decimal places, we look here and check the number to the right. It's less than 5, so we're going to round down, and it'll become 0.0006 after rounding to 4 decimal places. And I'll put a box on this one because I have some statements down below. This is the answer that we were going for. Kind of a heck of a problem. This one's tricky, and I think it's not necessarily the best exam problem because it takes time to decide were A and B really independent. We have to work through it, consider the situation. That's not appropriate for a 50-minute timed exam. But this is something that can happen on WebAssign, so watch out for these kinds of problems. Occasionally, WebAssign will tell you events are independent. Other times, we might have to determine that ourselves by just considering what the situation is. Well, we did it, folks. That's the end of the section 6.3 notes. Any last questions or comments on getting through these? Okay, it's definitely a slog, but congratulations. This is where I would definitely consider being over the hump in chapter 5, possibly for the entire course, depending on who you ask. Well, let's save this and let's take a look at section 5.4. I think we have enough time to make a little bit of headway into that section, but we won't get too far. So finally, 5.4 is conditional probability. Or can't do this because the dialog box is open. Okay. If you want the last time you copy. Sorry, Microsoft Word is just being ornery today. Okay, so here's our section on conditional probability. Now, we'll still do hypothetical 1,000 tables in this section, but it's not as many times. This table is already completely provided for in example 1. And looking at the context, it tells us a study from the University of Texas Southwestern Medical Center examined whether the risk of hepatitis C was related to whether people had tattoos and where they got their tattoos. That's a really specific word here, related. They didn't try to establish cause and effect. So they're not trying to say tattoos cause hepatitis C. That'd be a completely inappropriate statement. They would have had to do an experimental design. And that's almost impossible, right? You can't do an experimental design where you're separating out people. One group gets a tattoo at a parlor, one set of people gets a tattoo elsewhere, and these would be the control. That'd be a very unethical experiment. So at best, any conclusion they could put here is they might say, maybe having hepatitis C is related to having tattoos and where you got them, but that's as strong as a statement they could ever make here. So they go on to say, we have data from 626 participants summarized below. That's also a little bit different. We were doing hypothetical 1,000 tables, and when we were doing that, we expected to divide by 1,000 every time. Not here, because we have 626 participants. That would be the denominator in this problem. So section 5.3 is dangerous just because we get used to dividing by 1,000, but in 5.4, that would change up. So it now says, here's the random experiment. A random participant among the 626 is to be selected, and we'll round whatever values we come up with to 4 decimal places. So that's a setup so far, and we haven't even looked at this definition just yet. But we'll take a look at it once we're in part B. But for the moment, let's see what part B A is asking. It says, or asks, what is the probability that a randomly selected person in this study has hepatitis C? So I would write here, well, I'm thinking something along these lines. Probability of C. That makes sense, right? For having hepatitis C. In other words, we can call this event C, and this one C complement, just to help out to tie together the probability statement. The denominator is going to be 626. We're randomly selecting one amongst all of them. They'll all have an equally likely chance of being in the study. So our formula for equally likely events works again right here. But anyone see what should be in the numerator of this one? It wouldn't be a 1. Exactly. For hepatitis C, we're in this column and nowhere else. We could take the 8 plus the 17 plus the 22. But in this problem, there's no danger in just grabbing the total of 47. Since we're not going to be double counting anything at all, this is just one event, probability of C. There's 47 different ways to select a person that had hepatitis C in this study. And so that's our value right there. One big ugly looking fraction. We need to calculate this, put it in decimal form and round to 4 decimal places. So 47 division by 626 to 4 decimal places. Let me double check. Yes, 4 places. We get 0.0751. 0.0751. And then we've done it, folks. This says there's about a 7.5% chance of selecting one person amongst the 626 who would have hepatitis C in this study. Well, any questions or comments on that portion there? Okay, so essentially the things that we did with the hypothetical 1,000 table, we're still using that skill set here. Even if the table is different, a lot of those ideas still apply. Now, part B is finally quite a bit different. Here's where we will use the definition. But first, let's read through part B and just see what it's asking. They ask us, what is the probability that a randomly selected person has hepatitis C, given that this person does not have a tattoo? That word there is a massive buzzword. They don't always use it to indicate conditional probability. But if you see given that put in there, it probably is talking about conditional probability. So it says here that E and F are any 2 events. The conditional probability of E given F is donated by this probability statement right here. This is really just notation. Doesn't exactly tell us what conditional probability means. It doesn't tell us how to calculate it. It just tells us how to write down the probability statement. So this is what I would write. Well, first, we have 3 different ways to get tattoos. Let's put down some events for these things. Tattoo at a parlor, let's call it TP. So you have a tattoo, it was done in a parlor. Tattoo elsewhere, we can call this TE, meaning you have a tattoo, but it wasn't done at a parlor. Could have been done at home, maybe prison, who knows, but we just know you have a tattoo done elsewhere. For none, we could just say N if you like. So we have 3 different events going this way. Now let's run through this and see what the question is again. What is the probability that the randomly selected person has hepatitis C, given that this person does not have a tattoo? So we will write probability. The actual probability question is, what is your probability of getting hepatitis C? So I put that right here. Now what to do with given? That given produces the vertical line segment that you see right here in purple. I'll just kind of overwrite it in that way. So we get this purple segment here. Actually, let me try to get the right purple. Oh geez, I'm just scribbling on that. One last try. Okay, there it goes. Here's my given right here. So the given information goes into the second box right here. Does not have a tattoo. That's the event N that we indicated. So that's what we're calculating. Probability of C given N. Now, how do we calculate that? That's the major question now. And for each one of these questions, I'll use this table here as a screenshot to just show where I grabbed the data values from. Once I can get that screenshot to work. So it's going to be right here for part B. I'll put it down again here for part C when we get to that portion. Okay, so now we're in business to calculate this statement here. I want a specific kind of marker this time, or highlighter. We're going to use the FBI redacted pen. So when it says, given that this person does not have a tattoo, this is essentially what we've done to our data table. None of that information matters any longer. All we care about is person didn't have a tattoo and nothing else. Let me see if I can target that just a little bit better. So we are just in this row right here. Does that make sense to folks on why we're now fixating on just this row here? Awesome. In fact, even this total should be completely disregarded. It has no relevance, but we still need to talk about hepatitis C and not having hepatitis C because the probability question is about hepatitis C. So here's how it goes to this stage. We had to divide by 626 on part A because that was the sample size, or the sample space had size 626. But when you said given N occurred, our sample space is reduced to 513, just double checking I have the right number there. So now that's the sample space. We only care about people with no tattoos. 513 goes down below. Coming from right over here. And anyone see what should go into the numerator then? Exactly. We're asking for the probability of having hepatitis C. In this table, there are 22 different ways to get that because we only cared about people with no tattoo at all. So this becomes 22 513ths. Now, when we go to calculate this out, 22 513, we now have a probability of 0.0429 after rounding to 4 places, 0.0429. And that's pretty much the conclusion to this question. So conditional probability has this effect. We're calculating the probability of hepatitis C on the condition that all we care about is the people with no tattoos. We're eliminating part of the table every time you see a given like this, or every time you see the conditional probability format like this. Now, this is the probability that someone with hepatitis C, someone has hepatitis C given they don't have a tattoo, but we can give an alternative practical interpretation to this one. It wasn't required, so I'll put it in the orange pen as a comment. There's one way you can always interpret these. You could say there's a 4.29% chance randomly selected person had hepatitis C, given they had no tattoos. But sometimes there's a more preferred alternative to interpret this. It won't give us any better credit or less credit if we go for one or the other. But I think a lot of people just feel this makes more sense. So it's a better statement in that way. If I were to interpret this, I would say, first, let's go to the given information. Among all participants in the study with no tattoos, so we said the given statement first. Now we'll say this. Among people with no tattoos, there is a 4.29% chance that something happens. I'll skip over to here and say they had hepatitis C, that they had hepatitis C. By the way, that's the bad one. I think that's the one that will, over time, kill your liver. You could be in a really bad shape with hepatitis C. So that's why they're focusing so much on it in this particular study. Well, any questions, folks, on conditional probability so far? Okay, there's still much more to say, but if you feel comfortable with what we did right here, that's the big punchline to what's going to happen with conditional probability. We will have one problem that's a little bit more challenging than all the others, but I would say this is a pretty routine problem as far as an exam situation would go for this kind of topic. Well, any last questions then, folks, before we call it a night? Okay, well, have a wonderful weekend, folks. And we are getting close to the exam, so if you're studying over the weekend and you have questions, please don't hesitate to shoot them out to me through email. I'll be very happy to help out, even though it's the weekend.